ever, watch something like Star Trek or Star Wars, thinking about force fields or maybe teleportation, and wondered, well, could that stuff ever actually be real?
It's a great question, right? The kind of thing that really fires up the imagination.
Totally. So today we're doing a deep dive into Michio Kaku's book, Physics of the Impossible. It's a really thought-provoking read.
It absolutely is.
Our mission really is to unpack it for you. We want to explore that blurry line between science fiction and, well, actual science fact. We'll dig into Kaku's arguments, what got him interested, and some of the really mind-bending questions he asks about where science might be headed.
And it's important to understand this isn't just Kaku listing cool sci-fi gadgets. It's a proper scientific look at what could be possible down the line.
Right.
He argues pretty convincingly, I think, that while some things are probably always going to be impossible, other things that seem totally out there today, might actually become, normal in decades or maybe centuries.
He's basically taking us on a tour of that shifting boundary. How close are we, or how far, from making the impossible possible?
Exactly, and that really gets to the core message of the book.
Bitches.
Fundamentally, it's about redefining the word impossible. Kaku says that definition isn't fixed. It changes as our scientific understanding grows.
Okay.
Things that people once dismissed as pure magic, or maybe even madness, even top scientists, sometimes can actually become reality.
He gives some amazing examples of that, doesn't he? Historical ones.
He does. Think about a global communication network, or even the old alchemist dream of turning lead into gold. We can technically do that now in particle accelerators, just not efficiently. These were once just fantasies.
Yeah.
But they happened. And often, once the breakthrough comes, we kind of forget how impossible it seemed before. Kaku mentions Lord Rutherford.
The guy who discovered the atomic nucleus?
That's the one. He famously called the idea of getting energy from atoms in an atomic bomb basically moonshine. Utter nonsense, he thought.
Wow. And he wasn't alone in underestimating future tech, right? There was that whole thing with Robert Goddard, the rocket guy.
Oh, absolutely. Goddard faced so much ridicule, they called his work Goddard's folly. The New York Times actually published this really scathing editorial in 1921.
What did it say?
It basically mocked him, saying rockets couldn't work in space because there's no air to push against. They said he lacked the basic knowledge taught in high schools.
Ouch. That's embarrassing in hindsight.
Totally embarrassing. And the really chilling part, the first group to truly grasp the potential of Goddard's impossible rockets was, well, Hitler's regime. Their V-2 rockets, based on his principles, caused devastation in London during World War II.
So the impossible became horrifyingly possible.
Precisely. Kaku uses these examples to show why scientists have to keep questioning what they think is impossible. He even adapts that T.H. White quote.
Oh, yeah.
He says, everything not impossible is compulsory, meaning if no fundamental law of physics forbids it, it's bound to happen eventually, given enough time and progress.
That phrase really captures the book's optimistic spirit, doesn't it? So what got Kaku himself started on this path? What was his motivation?
It goes way back to his childhood, actually. He talks about watching reruns of Flash Gordon.
The old serials.
Yeah. He was just mesmerized by the technology, the rocket ships, invisibility shields, ray guns, those cities in the sky.
Classic sci-fi.
Exactly. He said it opened a whole new world for him. It got him excited about the possibility of traveling to other planets, exploring alien landscapes.
It's amazing how often science fiction sparks real scientific careers.
It really is. And Kaku points out that the huge leaps in science over the last century, especially quantum theory and Einstein's relativity, mean we can now, for the first time, make some rough, educated guesses about when some of these fictional technologies might actually appear.
So things like time travel or parallel universes, they're not just pure fantasy anymore.
Not entirely. Physicists are actually reevaluating them seriously now, thanks to things like string theory. The boundaries are definitely blurring.
Okay, so to help us navigate all this, Kaku came up with a classification system, right? Based on physics.
Yes, a three-tiered system. It's actually a really clear way to think about it, kind of like a roadmap for future science.
Let's break that down. What's the first category?
That's Class I, impossibilities. These are technologies we can't build today, maybe due to engineering limits or cost, but crucially, they don't violate any known laws of physics.
So theoretically possible, just really, really hard right now.
Exactly. Kaku thinks these could become real within decades, maybe a century or two.
And what kind of things fall into Class I?
This is where a lot of the classic sci-fi stuff lives. Think force fields, invisibility cloaks, phasers like in Star Trek, teleportation, maybe even telepathy or psychokinesis. Advanced robots, finding alien life, building starships.
Wow, that's quite a list.
It is. And what's fascinating is how fast some of these are moving. Kaku highlights teleportation at the atomic level anyway. Physicists used to say it was impossible because of Heisenberg's uncertainty principle.
Right, the whole can't know position and momentum thing. Star Trek even made up Heisenberg compensators to get around it.
They did. But now, with quantum entanglement, scientists have actually teleported quantum states, information encoded in light, over short distances. It's baby steps, of course, but it's real. The impossible is already becoming possible.
Okay, so that's class 1. What about class 2?
Class 2 impossibilities are the really big ones. These sit right at the edge of what we currently understand about physics.
Meaning?
Meaning, if these things are possible, it would probably require a major revolution in our understanding. Maybe finding new laws of physics or some kind of deeper unifying theory.
So what's an example of a class 2 impossibility?
Time travel is the big one he puts here. It's fascinating because even Stephen Hawking, who initially thought it must be impossible.
He tried to disprove it, didn't he, with that chronology protection conjecture?
Exactly. But he couldn't rigorously prove it was impossible. And that failure, that inability to rule it out completely, actually made physicists take time travel much more seriously.
Interesting. What else is in class 2?
Things like traversable wormholes for shortcuts across the universe and faster-than-light travel. These are concepts that really push the known limits of space-time and relativity.
Okay, pushing the limits. Then there must be a class 3, the really impossible stuff.
That's right, Class 3 impossibilities. These are things that seem to flat out violate the known fundamental laws of physics as we understand them today.
Like what? What's definitely off the table, according to Kaku?
He suggests these might stay impossible forever, or at least for thousands and thousands of years, unless our entire understanding of reality gets completely overturned. The main examples are perpetual motion machines.
Machines that run forever with no energy input.
Correct. And precognition knowing the future.
Why are those class 3?
Because they seem to directly contradict really solid principles, like the laws of thermodynamics for perpetual motion and the principle of causality cause preceding effect for precognition. These laws are considered foundational pillars of physics.
Gotcha. So, 3 classes. Possible but hard, possible maybe with new physics, and probably impossible forever?
That's a good summary. And Kaku structures the whole book around this. There are 15 chapters, and they're pretty much divided up according to these classes.
Right, the first 9 chapters tackle class I, the stuff that might happen sooner rather than later.
Exactly. He dives into each one, showing how ideas we know from fiction are actually being explored with real science and engineering even now.
So chapter 1 starts with force fields, not just the shimmering shields from Star Trek, right?
Right. He explains that while a pure energy wall is still science fiction, we have related technologies. He talks about things like plasma windows.
Plasma windows.
Yeah, developed back in the 90s at Brookhaven Lab by a guy named Adi Hershkovich. It uses super hot gas held in place by magnetic fields to separate a vacuum from air. And apparently it glows blue, kind of like those shuttle bay force fields.
Huh. Cool. And what about defying gravity, like hoverboards?
Ah, the Back to the Future dream. Kaku ties this to the potential discovery of room temperature superconductors.
If we found those, it would change everything.
Absolutely.
Mm.
He suggests it could enable things like magnetic levitation using diamagnetism, the same principle used to levitate frogs in super strong magnetic fields. Imagine wearing a superconducting belt and just floating.
Okay, my inner geek is loving this. What's next? Chapter 2.
Invisibility, making things genuinely unseen. He looks at natural examples, like how crystals can be transparent or how rapidly cooling glass works. But he makes a key distinction.
Stealth planes aren't truly invisible.
Exactly. They achieve radar invisibility by scattering radar waves, but you can still see them with your eyes. A true Harry Potter-style cloak, one made of flexible fabric, is incredibly difficult.
Why is that?
It needs a refractive index, how much it bends light that changes perfectly as the fabric moves. That's a massive challenge. Kaku thinks the first real invisibility cloaks will probably be rigid cylinders made of metamaterials.
But then there's the problem of seeing out, right? If light bends around you.
Good point. Kaku suggests maybe using tiny beam splitters near the eyes. Another approach he mentions is holographic camouflage, like work being done in Tokyo, where they project the background image onto the front of an object.
Clever. Okay, moving on. Chapter 3 sounds powerful. Phasers and Death Stars.
Yeah, this is about directed energy weapons. He traces the idea from H.G. Wells' heat rays in War of the Worlds, and even some early Nazi experiments with sound weapons, right up to the invention of the laser.
Lasers are real, obviously, but Death Star level power.
Well, consider the National Ignition Facility, KNIFE. It has 192 incredibly powerful laser beams. Together, they can deliver something like 700 trillion watts of power in a burst.
That sounds like a lot.
It's immense. Enough to start nuclear fusion, basically mimicking a hydrogen bomb explosion for a fraction of a second. But even that pales in comparison to a Death Star.
So what would a Death Star need?
Kaku says you'd need energy sources on a totally different scale, like massive magnetic fusion reactors or maybe nuclear-pumped X-ray lasers, an idea Edward Teller worked on for Reagan's Star Wars missile defense program. He also points out the terrifying power of natural gamma-ray bursts, which could sterilize a planet from light years away.
Okay, that's sobering. Let's shift gears. Teleportation. Beam me up, Scotty.
Kaku definitely acknowledges Star Trek made it famous. Apparently, it was originally just a cheap way to avoid filming expensive landing sequences. But he also addresses the serious scientific objections, mainly Heisenberg's uncertainty principle.
But you said earlier that scientists have achieved some form of teleportation.
Yes, quantum teleportation. Using quantum entanglement, they've teleported the quantum state, the information of particles like photons, over distance. They've even entangled light with atoms. It's not moving matter yet, but it's teleporting information, which was thought impossible.
Still feels like a huge leap to teleporting people.
Oh, enormous. Kaku references Douglas Adams's funny take with the infinite improbability drive, but also Stephen King's chilling story The Jaunt. In that story, teleportation works, but if you're conscious during it, your mind experiences an eternity of sensory deprivation. Only sedated people survive. It highlights the scary unknowns.
Yikes. Okay, next up. Telepathy. Mind reading.
Yeah, exploring the science behind it. Kaku contrasts the long history of fascination gods, psychics, even clever Hans, the horse that seemed to do math, with actual scientific attempts.
Like those card-guessing experiments.
Exactly. J.B. Rhine's Zener card tests. They showed some statistically marginal results initially, but they couldn't be reliably replicated, which is key in science.
And didn't the CIA try this stuff?
Oh, yeah. The famous or infamous Stargate project. They spent about $20 million over 20 years trying to use remote viewing to find people like Gaddafi or hidden plutonium.
Did it work?
The official conclusion was it provided no documented evidence of any useful intelligence. But Kaku does discuss more modern approaches, like using fMRI brain scans for lie detection. Research suggests lying takes more brain effort.
A perfect lie detector. Sounds useful, maybe.
Kaku raises a really provocative question. Would it destroy society? If all lies, even little white lies, were revealed, could our social structures even function? He calls it a potential social lubricant bomb, making interaction quite impossible.
Food for thought. Okay, next is psychokinesis. Moving things with your mind, like Carrie.
That's the idea. It's another huge trope in sci-fi and fantasy. From H.G. Wells' The Man Who Could Work Miracles, where a guy gets powers and accidentally stops the Earth rotating, oops, to Shakespeare's Prospero and The Tempest.
But in reality, spoon bending.
Kaku points out that things like Uri Geller's spoon bending have been widely debunked as stage magic. James Randi famously offered $1 million for proof of any psychic power under controlled conditions, and it remains unclaimed.
So, no mind over matter, then?
Not in that sense. But Kaku doesn't dismiss the brain's potential entirely. He mentions a Star Trek episode where powerful beings control energy with their minds. He also connects it, maybe more tangentially, to real-world tech, like the personal fabricators being developed at MIT machines that could potentially build almost anything, like a replicator, democratizing creation.
Interesting connection. Then we get to robots, the future of AI.
Yep. Kaku traces the history from ancient Greek automatons and medieval Islamic inventors like Al-Jazari, right up to Leonardo da Vinci's sketches for a robot knight in 1495. People have dreamed of artificial helpers for centuries.
But building truly intelligent ones is the challenge. The Turing test and all that.
Exactly. He talks about ambitious projects like CYC, which tried to manually program millions of rules for common sense into an AI. It turned out to be incredibly hard.
I remember hearing Marvin Minsky, one of the AI pioneers, say something about that.
Yeah, Kaku quotes Minsky, lamenting that AI can ace calculus but struggles to understand a simple children's story. There's a huge gap. Kaku asks a fundamental question. Will robots need emotions to be truly intelligent, to set their own goals? He quotes Dostoevsky, "If everything in the world were reasonable, nothing would happen."
Will they become conscious? Will we end up as their pets?
That's the million-dollar question, isn't it? The debate about machine consciousness is central and far from resolved.
Okay, two more in class one, extraterrestrial life and UFOs. Where are they?
Kaku starts by reminding us that Giordano Bruno was burned at the stake 400 years ago just for suggesting other stars might have planets. Now we know of thousands of exoplanets, how times change.
He also mentions Orson Welles' War of the Worlds broadcast.
Yeah, the 1938 radio play that caused panic because people thought it was a real news report of an alien invasion. It shows how culturally primed we are for the idea.
So the search continues. SETI.
Yep, the search for extraterrestrial intelligence. SETI projects mostly listen for radio signals around the waterhole frequency, 1.42 gigahertz, a natural frequency of hydrogen, thinking maybe other civilizations would use it too. So far, silence.
Which leads to Fermi's paradox. If the universe is so big, where are they?
Exactly. Kaku discusses possible answers, including the rare Earth hypothesis. This idea, from Peter Ward and Donald Brownlee, suggests that while simple life might be common, the conditions needed for complex life like ours might be incredibly rare.
What kind of conditions?
Things like having a large planet like Jupiter in the outer solar system to sweep up dangerous asteroids, and having a large moon like ours to stabilize the planet's axial tilt and climate. Maybe Earth is just cosmically lucky.
He also debunks giant movie monsters, right? The scale law.
Yes, he explains basic physics. An animal's weight increases with the cube of its size, but its strength, based on the cross-section of its bones and muscles, only increases with the square. So a King Kong-sized ape would simply collapse under its own weight. Physics puts limits on biology.
And he brings in the Kardashev scale. Civilizations based on energy use.
Right. Type 0 is us, using energy from dead plants, fossil fuels. Type I controls the energy of an entire planet. Kaku thinks we might be a century or two away from that, signaled by things like a global internet. Type 2 controls the energy of its star, maybe with a Dyson sphere. And Type 3 controls the energy of an entire galaxy.
A Type 3 civilization. They probably wouldn't even notice us.
Kaku suggests they might view us like we view ants in a forest. Maybe they're out there, but we're just too insignificant.
What about UFOs specifically? Does he think they're alien ships?
He takes a balanced scientific approach. He says about 95% of sightings can be explained as ordinary things. Swamp gas, meteors, weather balloons, secret military aircraft, radar glitches, like the Project Mogul balloon often cited for the Roswell incident.
But what about the other 5%?
He acknowledges there's a small percentage of sightings that remain genuinely unexplained. These often involve multiple credible witnesses, sometimes pilots or police, and are backed up by radar data. He mentions specific cases like the JAL flight over Alaska, the Belgian Triangles, an incident with an Iranian F-4 fighter jet.
So, unexplained but not necessarily alien.
Exactly. The key problem for science is the lack of repeatable physical evidence. No crash saucer in a lab, no undisputed alien artifact. Without that, it remains speculation, however intriguing.
Okay, final class I chapter. Starships. Getting to the stars.
He contrasts the historical pessimism some scientists in the 1920s said moon travel was impossible with the visionaries like Russia's Konstantin Tsiolkovsky, the father of rocketry. He also brings in Carl Sagan's idea that humanity needs to become a two-planet species to ensure long-term survival.
What about propulsion? How do we get there faster? Chemical rockets are too slow for interstellar travel.
Definitely. Kaku explores more advanced ideas, things like Vasima plasma engines, which could superheat hydrogen gas and potentially cut a trip to Mars down to months instead of years. Solar sails, using light pressure from the sun, are another option, though early tests have been tricky.
And the really futuristic stuff, fusion rockets.
Yes, like the Bussard ramjet. This theoretical engine, popularized by Sagan, would scoop up interstellar hydrogen as it flies, use it to fuel a fusion reactor, and expel plasma for thrust. In theory, it could reach a significant fraction of light speed, maybe 77%.
Imagine traveling to another galaxy.
A trip to Andromeda could take maybe 23 years from the perspective of the crew due to time dilation, even though billions of years would pass back on Earth. It's mind-bending.
He also mentions Project Orion, right? The nuclear bomb rocket.
Yeah, a real project from the 50s and 60s. The idea was to detonate a series of small hydrogen bombs behind the ship, pushing it forward with the shockwaves.
Sounds risky.
Extremely. It was eventually shelved, partly due to the Nuclear Test Ban Treaty, but also because of the obvious dangers: radiation, EMP, fallout.
What about space elevators? That feels very sci-fi.
It does, but it's a serious concept, tracing back to Tsiolkovsky and later popularized by Arthur C. Clarke and Robert Heinlein. The idea is a super strong cable stretching from Earth's surface up to geostationary orbit.
Held up by...
Essentially, the centrifugal force of a counterweight orbiting far beyond geostationary altitude keeps the cable taut. A NASA study suggested a cable made of carbon nanotubes, maybe 47,000 kilometers long, could slash launch costs from $20,000 per kilo down to maybe $2 per kilo.
But the material science isn't there yet.
Not even close. We can only make tiny carbon nanotubes currently, not continent-spanning cables. It's a huge materials challenge.
And Kaku also covers the dangers of long space trips, right? Besides just getting there.
Oh, yes. Weightlessness causes major problems, bone density loss, muscle atrophy as seen in long-duration stays on space stations. Then there's the constant risk of micrometeoroid impacts and the serious danger of radiation from solar flares and cosmic rays once you leave Earth's protected magnetic field.
What about solutions? Suspended animation.
He touches on it. While some animals can survive freezing, human cells tend to get damaged by ice crystals. But there have been experiments reviving animals after clinical death, so maybe some form of induced hibernation or torpor could be possible for shorter periods, reducing metabolic needs.
And nanobots, self-replicating machines.
Yeah, the John von Neumann probe concept. Tiny self-replicating robots sent out to explore. Kaku speculates they could, in theory, explore the entire galaxy in maybe 500,000 years by just making copies of themselves from materials they find along the way.
Okay, that wraps up Class 1. Now for the really weird stuff. Class 2, where we might need new physics.
Exactly. This is where things get highly theoretical, but also potentially revolutionary. He starts with antimatter and anti-universes.
He uses Dan Brown's Angels and Demons as a hook, right? The antimatter bomb.
Yeah, it's a great way to introduce the concept. Antimatter interacting with matter results in 100% conversion of mass to energy, according to Imsi Power. That's vastly more powerful than nuclear weapons, which convert less than 1%.
Where did the idea of antimatter even come from?
From the physicist Paul Dirac in the late 1920s. His equation describing electrons had two solutions, one for the electron and another that seemed to represent a particle with the same mass but opposite charge. That was the positron, the anti-electron.
And it was found later?
Yes, discovered experimentally a few years later. Dirac's equation also predicted electron spin, which is fundamental to electronics. Kaku jokes that Stephen Hawking wished Dirac had patented the equation. He'd be a trillionaire from all the computers and TVs using electron spin.
So if antimatter is real, why is the universe mostly matter? Where did all the antimatter go after the Big Bang?
That's a huge mystery. The leading theory, proposed by Andrei Sakharov, involves a tiny asymmetry in the laws of physics called CP violation. It suggests that in the early universe, for every billion antimatter particles, there were maybe 1,000,001,001 matter particles. After mutual annihilation, the tiny leftover fraction of matter formed everything we see.
Are scientists looking for any leftover antimatter?
Yes. Experiments like the Pamela satellite have searched for pockets of primordial antimatter, maybe anti-stars or anti-galaxies, by looking for things like anti-helium nuclei. So far, none found.
Does antimatter fall up or down? Anti-gravity.
Most physicists expect it to fall down, just like normal matter, obeying gravity in the same way. But it's incredibly hard to test experimentally because you need to make enough anti-hydrogen and keep it contained long enough to see how gravity affects it. Experiments at CERN are working on this, but it's tough.
What about anti-universes, mirror realities?
That specific idea related to parity or mirror symmetry was actually disproven in the 1950s by C.N. Yang and T.D. Lee, who won a Nobel for showing that the weak nuclear force violates parity. Kaku mentions Feynman's funny thought experiment. If you meet an alien, how do you know if shaking the right hand won't cause you both to explode due to opposite chirality? It matters.
Okay, from antimatter to wormholes and faster-than-light travel. This is pure sci-fi territory, surely.
You think so, but Kaku emphasizes that top theoretical physicists like Kip Thorne, Sir Martin Rees, and Matt Visser take these ideas seriously now.
Yeah.
Concepts like the Alcubierre warp drive.
Like the Millennium Falcon's hyperdrive.
Sort of. The Alcubierre drive involves warping space-time around a ship contracting space ahead, expanding it behind, so the ship itself doesn't technically break the light speed limit locally, but rides a wave of distorted space-time.
Sounds great. What's the catch?
The catch is it requires negative energy or negative mass to create the warp bubble, something with repulsive gravity.
Does negative energy even exist?
Surprisingly, yes, in tiny amounts. Kaku explains the Casimir effect, a real measured quantum phenomenon where two close plates in a vacuum experience an attractive force due to quantum fluctuations and the energy density between them is slightly negative.
But only tiny amounts.
Incredibly tiny. Like the negative energy measured is equivalent to maybe 130,000th the weight of an ant. So while it proves the concept exists, scaling it up to build a warp drive or stabilize a traversable wormhole would require unimaginable amounts of negative energy, technology potentially only accessible to a Type 3 civilization.
So possible in theory, impossible in practice for us.
Pretty much for the foreseeable future. Kaku suggests experiments like the Large Hadron Collider, searching for extra dimensions or evidence of quantum foam at the Planck scale, might give us clues about the underlying physics needed. Maybe tiny wormholes or baby universes pop in and out of existence at that scale.
Which leads perfectly into time travel, another Class 2 favorite.
Absolutely. Humans have dreamt of this forever. Kaku mentions early examples like Samuel Madden's 1733 book, Dickens' A Christmas Carol, Mark Twain's Connecticut Yankee, and of course, H.G. Wells' The Time Machine.
And you mentioned astronauts already do it slightly.
Yeah, due to Einstein's relativity, time passes slightly slower for objects moving very fast or in stronger gravity. Cosmonaut Sergei Avdeyev spent so long on the Mir space station that he aged about 0.02 seconds less than people on Earth. He traveled 0.02 seconds into the future.
Tiny, but real. And Hawking couldn't disprove travel to the past.
Right. His chronology protection conjecture aimed to show some law of physics prevents paradoxes, but he couldn't find a definitive proof. Kaku discusses theoretical time machine concepts, like rotating universes proposed by Kurt Gödel or infinitely long spinning cylinders. All require exotic conditions.
What about the paradoxes, killing your grandfather, that kind of thing?
Kaku introduces the main way physicists think about resolving this: the many worlds interpretation of quantum mechanics. The idea is that if you go back in time and change something, you don't alter your own past. Instead, the timeline branches off, creating a new parallel universe.
Like Doc Brown drawing on the chalkboard in Back to the Future.
Exactly like that. Causality is preserved in your original timeline because you've just jumped to a different one. Because time travel seems so intimately linked to the physics of wormholes and space-time warping, Kaku firmly places it in Class 2.
And that naturally leads to the next chapter, parallel universes.
Indeed. Kaku uses the famous Star Trek Mirror Mirror episode with the evil goatee Spock as a familiar entry point to the idea of alternate realities existing alongside our own, possibly in higher dimensions.
Higher dimensions, like beyond length, width, and height.
Yes. While common sense tells us we live in 3 spatial dimensions, advanced theories like string theory and its successor M theory actually require extra spatial dimensions to work mathematically.
Where are they then?
The idea is they might be curled up incredibly small, at the Planck scale, far too tiny for us to perceive directly. Or maybe our universe is a 3D brain floating in a higher dimensional bulk. Kaku explains how M theory, proposed by physicists like Edward Witten, unified 5 competing string theories by adding an 11th dimension.
Could we ever detect these extra dimensions?
Possibly. Experiments at the LHC looking for particles like sparticles, supersymmetric partners of known particles, could provide indirect evidence if those particles are leaking off into other dimensions.
What other reasons are there to believe in parallel universes?
Kaku discusses the anthropic principle. The constants of nature in our universe seem exquisitely fine-tuned to allow life to exist. Change gravity or electromagnetism just slightly, and stars or atoms couldn't form. Why is our universe so perfect?
Maybe it's just luck.
Or, as Sir Martin Rees and others argue, maybe our universe is just one of an infinite number of universes in a multiverse, each with different physical constants. We just happen to live in one where the conditions are right for us. It sidesteps the need for incredible luck or a designer.
And this connects back to the many worlds idea from time travel.
Yes, Hugh Everett's interpretation of quantum mechanics. Every time a quantum measurement is made, instead of the wave function collapsing to one outcome, the universe splits, and all possible outcomes occur, each in its own parallel reality. As physicist Alan Guth quipped, somewhere out there, Elvis is still alive. Al Gore is president.
It's almost too much to comprehend. Infinite branching universes.
Kaku even explores ideas like baby universes budding off from ours, or Edward Harrison's concept of natural selection among universes. Maybe universes that are good at producing black holes which might spawn new universes are the ones that proliferate, and maybe those conditions also favor life. It gets very speculative, but it's grounded in cutting-edge cosmology.
Okay, deep breath. Let's move to the final category. Class 3. The stuff Kaku thinks is probably impossible forever.
Right, things that seem to break fundamental laws. Chapter 14 is perpetual motion machines.
The dream of free energy.
A dream people have chased for centuries. Kaku recounts the history. Patents filed since the 1600s, elaborate trick machines built by people like Johann Bessler, even sketches found in Leonardo da Vinci's notebooks, though da Vinci himself publicly dismissed the idea. It got so bad the French Academy of Sciences stopped even looking at perpetual motion proposals in 1775
Why are they impossible?
because they violate the laws of thermodynamics, which emerged partly because all these machines failed. The first law says energy can't be created from nothing. The second law says entropy, disorder, always increases, meaning heat only flows spontaneously from hot to cold, and no machine can be 100% efficient. Some energy is always lost as waste heat.
What about clocks that run on atmospheric pressure changes?
Kaku mentions those, like John Cox's clock from the 1760s. But he points out they aren't true perpetual motion machines because they are drawing energy from an external source, the changing environment. They aren't creating energy out of nothing.
And these laws are considered pretty solid.
Rock solid. Kaku connects them to Emmy Noether's profound theorem from 1918, which links conservation laws directly to symmetries in the universe. For example, the fact that the laws of physics don't change over time symmetry, mathematically implies the conservation of energy. To break energy conservation, you'd have to break the symmetry of time itself.
Okay, perpetual motion is out. What's the final Class 3 impossibility? Chapter 15.
Precognition. Knowing the future, seeing events before they happen.
Another timeless human fascination.
Prophets.
Oracles.
Exactly. Kaku mentions the Greek myth of Cassandra, cursed to see the future but never be believed. He talks about historical figures like Nostradamus or Edgar Cayce, whose prophecies were often so vague they could be interpreted to fit almost anything after the fact. He even cites a supposed 9/11 prediction as an example of this post hoc fitting.
People still make predictions today, though. Doomsday dates.
And they consistently fail, sometimes causing mass panic. Kaku gives examples, like a predicted flood in 1524 that led to riots when it didn't happen, or the Millerite movement in the 1800s, predicting Christ's return, whose followers eventually formed groups like the Seventh-day Adventists after the prophecies failed. History is littered with failed predictions.
Is there any physics that even hints at seeing the future?
Kaku discusses some exotic theoretical ideas, like tachyons, hypothetical particles that always travel faster than light. If they existed, could you use them to send messages backward in time? Some physicists have seriously considered this.
If you send yourself lottery numbers.
Probably not. Kaku concludes that even if tachyons exist, the laws of physics would likely conspire to preserve causality. You probably couldn't create paradoxes by sending information that changes the past in a way that prevents the message from being sent. The universe seems to protect itself from paradoxes.
So precognition is firmly Class 3.
Very firmly. Kaku states that if repeatable, controlled experiments ever genuinely proved precognition exists, it wouldn't just be amazing, it would fundamentally shake the foundations of modern physics. It would require a complete rewrite of our understanding of time and causality.
Right. So we've covered the 3 classes and the specific examples. Let's think about the bigger picture, the key scientific figures and concepts that underpin all this.
Yeah, Kaku constantly refers back to the giants. Einstein is everywhere, obviously, with general relativity being crucial for wormholes, black holes, time dilation. Newton sets the classical stage, though Kaku notes string theory might solve infinities that arise in Newton's gravity. Heisenberg and his uncertainty principle form a key hurdle for teleportation.
And the quantum pioneers.
Absolutely. Paul Dirac predicting antimatter, Erwin Schrödinger and his famous cat paradox illustrating quantum weirdness, Wolfgang Pauli predicting the neutrino decades before it was found, showing how theoretical insight can lead experiment.
Then the cosmologists and futurists.
Stephen Hawking on black holes and time travel, Carl Sagan for popularizing things like ramjets and SETI, Freeman Dyson with his ambitious ideas like Dyson spheres and Project Orion, and Arthur C. Clarke, whose science fiction often felt like blueprints for the future, with space elevators and railguns.
And for AI?
Alan Turing and the Turing test. John von Neumann and self-replicating machines. Marvin Minsky, highlighting the real challenges in achieving common-sense AI.
So these figures and their ideas, quantum mechanics, relativity, antimatter, dark matter, superconductors, fusion, they're the toolkit Kaku uses.
Precisely. He uses them to show how that line between sci-fi and science fact keeps shifting. Ideas that were once dismissed or even punished, like Giordano Bruno and other planets, are now confirmed facts.
Or theories that seemed untestable, like atoms or neutrinos, eventually get proven.
Right. It builds his case that today's impossible might just be waiting for the right theory or the right experiment. It's a history of science lesson embedded in future speculation.
The book is full of memorable quotes, too. You mentioned one earlier, everything not impossible is compulsory.
Yeah, that's Kaku's adaptation of T.H. White. It really captures the book's core optimism. If physics doesn't forbid it, it's ultimately achievable. It's a challenge to be bold.
But he balances that optimism, right, with that Niels Bohr quote.
Yes, prediction is very difficult, especially about the future. It's a necessary dose of humility. Science is unpredictable. Big breakthroughs often come from unexpected directions. It keeps the speculation grounded.
And there was that question from Kip Thorne you mentioned about wormholes and time machines.
Right. Do the laws of physics permit very advanced civilizations to create and maintain wormholes for interstellar travel and to build time machines for backward travel in time?
Why does that one stand out?
Because it takes the most extreme Class II ideas and frames them as a serious question about the ultimate limits of physical law. It asks, could the universe itself allow for these ultimate technologies, perhaps only for civilizations far beyond our own level, like a Type 3? It connects fundamental physics to the grandest possible future engineering.
It feels like the book isn't just about physics, though. It touches on deeper philosophical things.
Definitely. There's a strong current of techno-utopianism, the idea that science and technology are the keys to solving problems, expanding humanity's horizons, reaching for those higher Kardashev levels.
And the time travel and parallel universes stuff that gets into determinism versus free will, doesn't it?
Absolutely. If all possible timelines exist in the many worlds scenario, what does that mean for choice? Can you really change your destiny or just jump to a different predetermined track?
The AI chapters definitely feel like they're heading into posthumanism, questioning what makes us unique if machines can think or feel.
For sure. And Kaku subtly highlights the ongoing tension in science between empiricism, only trusting what you can measure, and theoretical leaps based on mathematical beauty or intuition, like with atoms or string theory. That struggle drives progress.
How does this connect to issues we grapple with today?
Well, the ethics of AI is a huge one. His point about lie detectors potentially destroying social trust is very relevant with advances in neurotechnology and surveillance. The idea of pre-crime based on brain scans raises massive liberty concerns.
And the nature of consciousness itself, that's a major debate in neuroscience and philosophy right now.
Exactly. Kaku admits we don't even have a solid definition, let alone know if machines can achieve it. The paradoxes of time travel, while theoretical, force us to think about causality and reality in deep ways.
And the whole discussion about humanity's future, the Kardashev scale, the rare earth hypothesis, it speaks to our anxieties about long-term survival, climate change, finding our place in the cosmos.
And these aren't just abstract ideas.
Yeah.
The search for exoplanets is happening now. SETI is ongoing. The LHC is actively testing theories about extra dimensions. Quantum computing research is advancing rapidly. The book connects directly to cutting-edge science.
Okay, let's step back and look at the book critically. What are its biggest strengths?
I think number one is accessibility. Kaku is just a brilliant communicator. He makes incredibly complex physics understandable and exciting for almost anyone without dumbing it down too much.
He uses analogies and pop culture references really effectively.
He does, which ties into another strength, imaginative thinking. He bridges the gap between rigorous science and wild sci-fi possibilities in a way that feels inspiring, not just speculative.
And it's always grounded in real science, right? He's careful to explain why something is class 1, 2, or the third based on known physics. He cites real experiments and researchers.
Definitely. He builds his case logically, using historical precedents effectively.
What about potential weaknesses or limitations?
Well, sometimes the speculative leaps feel pretty big, going from lab-scale quantum teleportation to beaming people across space, or from tiny carbon nanotubes to a space elevator. The engineering challenges are glossed over sometimes.
Understandable for a popular science book, maybe, leading to a lack of technical depth in some spots.
Possibly. If you're a physicist, you might want more mathematical rigor, but that wasn't the goal. Also, the timelines, decades or centuries, can feel a bit optimistic given the scale of the challenges.
And the untestable challenge you mentioned, some ideas, like the multiverse or string theory, are currently beyond our ability to prove or disprove experimentally.
Right. Kaku argues that's often been true of revolutionary ideas in the past, but it's still a valid point about the limits of current science for some of his farther-out speculations.
Could anything have been explored more deeply?
Maybe the sociopolitical ramifications. He touches on ethics. But what would ubiquitous invisibility cloaks or cheap fusion power actually do to global politics, economics, warfare? That could be a whole other book.
The resource constraints, too. Building Dyson spheres or galactic empires takes unimaginable amounts of matter and energy, Where does it come from?
Good point. And maybe more on the human adaptability side, the psychological toll of centuries-long star voyages or living entirely disconnected from Earth. The human element beyond just the physics.
So, we've taken quite a journey ourselves through Kaku's landscape of the impossible, from things like force fields and robots that feel almost within reach, to the truly mind-bending ideas of time travel and other universes.
It really underscores how science is constantly pushing boundaries, turning yesterday's fiction into tomorrow's potential reality. What seems impossible is always changing.
Which leaves us, and you, with a final thought to ponder. As we consider all these incredible and sometimes terrifying possibilities, if teleportation, invisibility, or even time travel one day become realities, will we be prepared for the ethical, societal, and existential consequences they bring?